Hi, everyone. Thanks for joining us today on this day that feels a little more like January than like October, like the last couple weeks where it's been nice and a little bit warmer. Here in Western Wisconsin, we have not that much snow, but enough right now for my kids to go sledding and get some time outside anyways. So welcome to our final webinar as part of our 2020 and now 2021 Virtual Discovery Farms Conference. Our theme for this conference series has been keeping up with your conservation goals through change and challenge. It's been brought to you by Discovery Farms programs in Minnesota and Wisconsin and the many organizations that support these programs, including those you see on your screen now, who have helped us out with sponsoring this conference specifically this year. Discovery Farms is a water quality research and educational program that focuses on the intersection of agriculture and water quality and stresses the importance of farmer leadership. And we, in Wisconsin and Minnesota, follow those same pillars and are able to share data across state lines and work together as to help serve farmers and farm advisors in both states. For those of you that are hoping to get CCA CEU credits, at the end we'll show the QR code, and in order to get your credits you can use the QR code or put your CCA number in the chat and we can help you out with that. If you've been following along or participating with us through the last 7 weeks or so as we've had our webinar series, today's webinar will work a little bit differently. So here are your steps for today. If you've not done so already, please mute your mics and cameras, except for the speakers, of course. And for the first 30 minutes or so, we'll hear short talks from each of our 3 speakers. Questions during that portion will be taken via the chat box. This part of the session will be recorded and will be put on Facebook Live and YouTube. So we need to make sure that we don't have folks talking over one another or sharing their videos. So that's for the first section. During the second half of the hour, we'll put each of the speakers into their own breakout room, and you're free to join in discussion with them, unmute yourself and ask questions, share your experiences, and even enter different rooms during that time if you'd like. At the end, we'll reconvene here in the main breakout room for CCA credits and some final closing notes at the end of the session. You should be able to choose your own breakout room through the breakout room button on the bottom of your screen. If you have difficulty with that, we'll be happy to assign you to a breakout room and help you out with that. Today, we designed this final webinar in the series to help apply some of the topics discussed in previous webinars to actual farm management. So the 3 speakers we have today are Timothy Griffis, Matt Ruark, and Erica Gentry. We're going to start with Dr. Griffis. He is a professor of biometeorology at the University of Minnesota. He has a PhD from McMaster University in Ontario. And from early discussion, it sounds like he's a bit of a Packer fan, even though he grew up in our friends to the north, with our friends to the north in Canada. Tim's recent work has been focused on reactive nitrogen in the atmosphere related to cropping systems, and he has some very valuable information to share regarding carbon and nitrogen dynamics here in the US Corn Belt. And the carbon piece and nitrogen piece are very relevant with all this talk now we're hearing about climate change and things like that. So we're going to start with you, Tim. Thanks for being here. We're excited to hear from you.
Oops, here, just trying to share my screen. Of course, here we go. Thank you so much, Amber, for the introduction. I want to thank Warren and Erica for organizing this and for the invitation to speak today. So can everybody see that? Is that good?
That's great.
Okay, great. So this has to be a lightning talk, so I'm going to go a little bit quick here. And I'm going to give you sort of my atmospheric top-down regional perspective on reactive carbon and carbon dioxide in the atmosphere. So back in about 2007, I was very fortunate to receive funding from the National Science Foundation that allowed us to instrument this tall tower that you see in this photo. So this is a 244 meter tower, I think roughly about 800 feet. And from that tower, we pull air samples down from the top on a near continuous basis. We've been doing this since 2007 and analyzing things like nitrous oxide, ammonia, carbon dioxide, methane, and other gases in our atmosphere. This gives us a regional perspective. The footprint or the source area of this tower is very large. It gives us a window into the upper Midwest and US Corn Belt. So we can keep track of how climate and land management and other sort of activities that influence the surface are influencing the composition of our atmosphere. And so today I'm going to sort of rely heavily on those tall tower observations, but I want you to know that out here in the footprint, we also have some other systems working, eddy covariance systems that are looking at the carbon dioxide exchange between the land surface and the atmosphere. We also use the Weather Research and Forecasting Chemistry NCAR model from the National Center of Atmospheric Research to help interpret these atmospheric observations. And then with the support of the Minnesota Corn Growers Association over the years, they've been helping us conduct mesocosm simulations indoors so that we can look at climate and land management impacts on these trace gases. Okay, so here's just a close-up perspective. I want to give you an idea of what the kind of measurements we're making. This shows you the tall tower. You can see it's heavily guided, and we have air samples that are constantly bringing down the air using these very large vacuum pumps. Once the air gets into the building, our manifold and calibration system routes that air, and we calibrate that and analyze that air sample using these tunable diode lasers. So the laser you see here is looking at methane. The laser you see here is measuring carbon dioxide and nitrous oxide concentrations. And since about 2007, we've made over 100,000 hourly observations for CO2, about 90,000 observations or so for nitrous oxide. So this is important because it provides a benchmark for understanding how those concentrations are changing in the atmosphere and how things like climate might influence their composition over time. We also need a benchmark if we start to use mitigation strategies. We're going to want to know how effective those things are. So this allows us to look back in time and see if we're improving or if things are getting worse. Okay, here is a nice long-term, this is a very unique record of nitrous oxide concentrations in our atmosphere. And as all of you know, at this point, nitrous oxide is a very important greenhouse gas. It's about 265 times more effective at absorbing infrared radiation or thermal radiation compared to the carbon dioxide molecule. So it's very important with respect to the greenhouse effect. It is also now the #1 anthropogenic emitted chemical implicated in destroying stratospheric ozone. And that's important because that ozone layer is protecting us from harmful UVB. As you can see, the trend, our tall tower rate of increase in concentrations is about 0.7 parts per billion per year. And that's right on pace or in good agreement with the global rate of increase as well. And so the reason that the nitrous oxide concentration is going up over time is because of the increased use of nitrogen fertilizers. And one of the byproducts of denitrification and nitrification is this nitrous oxide molecules. You can also see from these hourly data that we have a lot of what we call hot moments. Early in the spring, you see these flashiness of large emissions of nitrous oxide as the soil thaws. Sometimes in the summer when we have a big rain event, especially right after fertilizer has been applied to a lot of these farm fields, we see these big pulses of nitrous oxide to the atmosphere. And so basically, we're monitoring this. We know that this is a strong signal from the US Corn Belt, and we want to figure out ways of how to reduce these nitrous oxide emissions. In 2017, we had the opportunity through another NSF grant to expand our reactive nitrogen work, and we started adding measurement systems from Los Gatos and Picaro that allow us to measure ammonia concentrations in the atmosphere. Now, ammonia is not so important climatically. It's not a greenhouse gas, but it's very important with respect to the formation of PM 2.5 in the atmosphere, and then sort of respiratory problems and sort of health impacts. And I'll just show you a little sample of these data. So we've been doing this for 4 years now, and you can see, as you would expect, a sort of steady rise of ammonia following fertilizer application in the spring. And then a really interesting thing that we see is the rise of ammonia in the atmosphere in the late fall, which we associate with manure application in our region. In 2017, I remember stories being written in the Star Tribune about the very bad air quality, and everybody was complaining about the sort of pungent smell in the atmosphere. And at that time, I was looking at our tall tower data and seeing that our ammonia concentrations were really skyrocketing. And this happened again in 2020, and it kind of times out with, after that application of manure, if we get a strong warm up in temperature, we see this volatilization increase, and we see this sort of large flux of reactive nitrogen into our atmosphere. So very sort of interesting example of how managing the land and the interaction with climate can influence how much nitrogen we see going into the atmosphere. Our best estimates, when we do what we call inverse regional budget analysis, we are estimating about 316 to 585 gigagrams of nitrogen per year are going to the atmosphere via the Corn Belt. And for ammonia, it's significantly larger, over 1,000 gigagrams of nitrogen per year. So this brings us up to a total of about 1,800 gigagrams of nitrogen per year, or roughly 23% of the amount of synthetic nitrogen inputs to the US Corn Belt. And so the interannual variability and variations that we see over time tell us that this is very sensitive to temperature and precipitation. So for example, in 2012, we had one of, I think, the warmest spring on record for our region. And this resulted in the largest emissions of nitrous oxide to the atmosphere that we've ever seen in our record. So there's a very important climate story here, and that it could be warmer and wetter conditions could be enhancing nitrous oxide emissions to the atmosphere. Okay, very briefly, we've been measuring carbon dioxide in the atmosphere even longer than nitrous oxide. And this upper panel I'm showing you, every dot you see is an hourly data point of carbon dioxide that we measured at the tall tower. From these data, you see this very strong seasonal signal. In the non-growing season, we see CO2 concentration rise because of things like ecosystem respiration and some other anthropogenic contributions. But during the growing season, you see the concentration of carbon dioxide in our atmosphere get very low. We say that this has a very, there's a very large amplitude in the CO2 concentration going from sort of the largest values to the lowest values you see in the summertime. We know from satellite analysis of chlorophyll fluorescence, sun-induced chlorophyll fluorescence, and these kind of carbon dioxide measurements that the US Corn Belt is one of the most productive regions in the world, largely because of the large corn acreage. So it sucks a lot of carbon dioxide out of the atmosphere. We're getting drawdowns all the way to about 340 parts per million. The global average concentration of carbon dioxide now is a little bit over 400 parts per million. What's alarming, or what's potentially very important here, is when we look at that amplitude and how it changes over time and how it responds to temperature, we are concerned that these croplands, their productivity is being limited by warmer summer, especially July, August temperatures. And we're projecting that a future increase in summer temperature based on sort of business as usual emission scenarios, the so-called sort of IPCC emission forecasts, our data suggests there could be a 10 to 20% reduction in the amount of CO2 that's sequestered within the US Corn Belt, suggesting that perhaps we've approached, or we may be surpassing sort of the thermal optimum or the optimal conditions for photosynthesis. Okay, if I'm going to narrow the scope a little bit, and we're going to bring it right down to the field scale. John Baker and I have been making eddy covariance measurements of CO2 in a conventional corn and soybean system for many years. And this graph here shows you the cumulative amount of carbon dioxide exchanged over time. And you can kind of see from this graph, when we have a soybean year, we see this kind of productivity. And when we have a corn year, we have much greater productivity. But overall, we're trending away from the net carbon balance line. And if we accumulate all of this sort of CO2 exchange data that we've acquired since way back here in 2007, we're posting a net loss of carbon to the atmosphere of over 1,000 grams per meter squared. So that's a significant loss. This graph that you see here accounts for the carbon lost after grain harvest. Okay, so my little question, probably relevant for our breakout group, is climate conspiring against our best efforts? We see that nitrous oxide is enhanced by warmer temperatures, increased springtime precipitation. We see that the carbon dioxide flux into ecosystems is being dampened by the fact that we're getting warmer summertime conditions. So this leads me to the final part of my lightning talk here. We've been using indoor mesocosm simulations to help understand how to better manage agricultural systems, mainly from the perspective of how can we reduce reactive nitrogen losses. So we have been doing scenarios that look at the effect of enhanced precipitation, and what we see is generally slightly increased loss of nitrous oxide from these systems, given sort of current trending, sorry, I should say future climate change scenarios with an increased springtime precipitation. And we're also beginning to play with Pivot Bio, sort of these engineered, custom designed microorganisms to help reduce the amount of reactive nitrogen loss in the form of nitrous oxide to the atmosphere. So these are sort of ongoing experiments that we are performing in the greenhouse to get a better understanding of how climate will impact these systems. So with that, I just want to say thank you for the invitation today. I want to thank the Minnesota Corn Growers Research and Promotional Council, National Science Foundation, USDA, and Minnesota Public Radio, who allows us to use their very tall tower communications facility. So thank you.
Excellent. Thanks, Tim. We do have one question for you that came in through the chat. What do you think about, would manure composting reduce ammonia escape? Like if it was composted, then land applied?
So I do think that will help. We've actually done a few experiments in the mesocosm facility to look at how manure influences ammonia versus nitrous oxide. Very important trade-offs here. We saw that nitrous oxide actually went up when we applied manure, but the ammonia was down with proper treatment and incorporation into the soil profile.
Trade-offs, always the devil
yes.
in the details. Yep. Okay, so I see we have one more question, but that's from Tim. So I'm going to ask that I copied it down, Tim, and that's going to be for the breakout rooms. So
Great.
It was from Tim Raditz to you, Tim Griffis. So I'm going to relegate that one to the breakout rooms.
Thank you.
Okay, so yeah, thanks, Tim. I really appreciate it. That was great info. Okay, let's see. Tim, can you stop sharing your screen? And then next up, we'll have Matt Ruark. Matt, are you? Yes, there. Okay. Matt, I'm going to introduce you quickly. So Matt is a professor of soil science at the University of Wisconsin-Madison. He specializes in soil fertility and nutrient management and has partnered with Discovery Farms for more than 10 years and recently had a large role in guiding the nitrogen use efficiency project, of which today he's going to talk about specifically the zero end strips related to that. Matt, I can see your presentation.
Thank you.
And I can hear you. Great, thank you.
All great things. Okay, so perhaps some of you have seen us do presentations on nitrogen use efficiency. We've created some benchmarks based on just inputs and outputs, right? What's your yield based on the nitrogen you applied? But the next level is this idea of putting in a zero nitrogen test strip. And so I'm going to give a short presentation on our, well, basically we're promoting the use of the zero N test strip as a valuable metric. Now what would we use that for? So if you're going to put a strip of corn in where you're not, and then you're going to skip a fertilizer application of what are we trying to get at here? So we can get at two things. We can get at the agronomic efficiency and the uptake efficiency. And then to answer these specific questions, how much did the nitrogen applied improve productivity? So a lot of times we give the full yield. So the fertilizer gets credit for the full yield, but that's not really true. It only gets credit for the yield gain. And this is how we would calculate that, right? So the idea of we're going to take what's that yield difference between when you apply fertilizer and not. And then it's the nitrogen applied minus the N applied in the zero test strip. So usually that's zero. So what's the yield gain per nitrogen applied? The other aspect that we can do is we can think about how much of the nitrogen that was applied ended up in the plant. And this is where we're going to talk about this in terms of uptake efficiency. So that's the uptake, that's the total nitrogen uptake in a plant that was fertilized. And you subtract that off the total N uptake in the plant that wasn't fertilized, you divide that by the amount of N that was applied. So this value, this value right here, this nitrogen uptake, total nitrogen uptake in pounds per acre when fertilizer wasn't applied, represents the nitrogen that comes from mineralization of soil organic matter, comes from residual nitrate, maybe left over from the previous season, decomposition maybe of some crop residues, those sort of things. If you're under irrigated conditions, you might have some nitrogen coming from those kind of background levels. So it gives us two options. And then I like to put this graph in, and this is sweet corn. I do this with every crop I study, but you can think about like you're getting, it's this yield gain or the extra nitrogen uptake that occurs. So we're trying to figure out what's the real value of the fertilizer for that field. So this is part of a bigger study where we benchmark nitrogen use efficiency, and we've worked across 15 counties with 85 farmers, 300 fields in total for all these assessments. But not every field has this zero N test strip. So in the end, we were able to get 55 fields to test this in for corn grain. And so we can look at these ranges and values. So first off, we're going to note it's quite variable. So every single field, there's no universal trends, right? Every field is its own special entity to think about and needs to be evaluated separately. On average, we're seeing for an agronomic efficiency, we're producing about half a bushel of grain per pound of N applied, or we get a half a bushel of yield increase, I should say, for a pound of N applied. For uptake efficiency, we see about, on average, 58% of the total nitrogen that's applied as fertilizer is ending up in the plant. That's pretty good. We're seeing, but we're seeing a quarter of our fields have 80% or more. And so that's actually really, that's a pretty high value. So this is, the higher the values here, the more, it means the more of the nitrogen that was applied was actually utilized by the plant, and thus reducing the likelihood that we'll have leaching losses of nitrogen. But you can see, like, we've also got a quarter of all the fields that we tested where less than 40% was used. So the variable in the data suggests that every field, soil, and systems are different. And so when we're thinking about where you're ranking on this, if you have high efficiency or low efficiency, well, primarily if you have low efficiency, that would be the trigger of like, okay, what should I think about doing? Maybe this means I should test some other options for my nitrogen management. We also had 17 fields where we evaluated corn silage. So corn silage always does really well when you look at overall efficiency because we remove so much nitrogen from the system. But what here we're looking at, we have quite a range in agronomic efficiencies here. And then we're seeing for corn silage production about on average around that 50% of the nitrogen that's applied is taken up, with the highest 25% of the fields having 70% of that nitrogen that's applied actually taken up. And so these are really important numbers, and it's that percentage really gives us a sense of that water quality implication of your cropping system. So a lower utilization efficiency means a higher percentage of the applied N was not taken up by the crop and is susceptible to leaching. So if we graph stuff out on this basis, so as we see, we're increasing the uptake efficiency, and in some cases we had even greater than 100% efficiency for various reasons. But in some cases we had, that 75 to 95% efficiency. When we have those really high efficiencies, we're seeing that the amount of N that's not taken up is relatively low. So as you decrease in efficiency, then we're getting a lot of nitrogen. In some cases, in some fields, we had over 100 pounds of nitrogen that wasn't even taken up. And so clearly that's not a value to the environment, and clearly that's not value to productivity. So we have all of those, and every farm field. So we're promoting those as important or as valuable metrics. However, we can also do something. You don't have to go with a full zero rate. So we also had some farmers that were using what we're calling low nitrogen test strips, or a half nitrogen test strip. So again, this is different than the full, the true zero, but it can still be useful. So for example, we had this farm field where we had the low nitrogen test strip that had 82 pounds of nitrogen out there that came from a clover legume that was plowed under, as well as some nitrogen from manure. And so we're crediting both those things as 82 pounds of nitrogen. Then on top of that, they applying 113 more pounds of nitrogen on top of it to bring themselves up to 195 pounds of nitrogen for that field. So this is basically with an in-season nitrogen fertilizer application on top of just the legume and manure credits. So without any additional N, they got 175 bushels. With this additional N, they got 208 bushels. So they applied 113 extra pounds of nitrogen to get an extra 33 bushels. So what does that mean in terms of productivity? It means that for economic profit loss, assuming that we have $3 corn and 40-cent nitrogen, still was profitable to apply nitrogen. We made $54 an acre, and that's always some of the trick with the economics here, because with relatively inexpensive nitrogen. But when we look at the partial factor productivity, it ended up being in that low to low mid use efficiency. So overall, it wasn't particularly an efficient system when we looked at the overall system. And the uptake efficiency was only 22.5%. So of this 195 pounds of nitrogen the 113 pounds of nitrogen that got applied, only 22% of that ended up in the plant. And we had 88 pounds of unused nitrogen. So this would indicate, one, is that this was not, even though it was profitable, it still wasn't the most profitable or the most efficient system. So, and this is a case where, there's a lot of detail, in how they applied that 113 pounds, but could they get by with less nitrogen? Could they change the timing, the source of that nitrogen to improve efficiency? But it does appear that there would be some improvements in efficiency, that there's a potential for improvements to be made, right? And really, it's hard to really assess this without putting out these strips. And the last thing we'll show is that here's a graph where we put everything together. And so in the red dots we'll start with the x-axis here. That's the increase in yield for any one site. So again, we have all of these sites that have these varying increases in yield relative to nitrogen application. We also put out, in the blue, here's the low test strips, the gain in yield with putting out, already starting with a low nitrogen application. So you can see we have this wide range of increase in yield across all these fields. So which one are you? Are you the one that's getting this huge bang for the buck with fertilizer? Are you in the medium range? Are you in the low or even the negative efficiency range? So without putting out the strip, it's hard to know. So in any case, but what's also interesting is that we have this range of yield increases, right? As we're going this direction on the graph. And so is this a case where we're just getting the benefit on high yielding fields where, is it just yields go up when it's a higher yield potential soil? But what you can see here, we also graphed on top of this, the increase in yield relative to the maximum yield that occurred in each field. So you can see that we can have high gains in yield or low gains in yield, regardless of the yield potential of the soil or the ending total yield. So as we think about this, so it's not just your high yielding fields, it's not just the low yielding fields you should do this on. It appears like this effect is going to could occur across all types of fields. So with that, I think I'll wrap up there. Look forward to some good discussion. And as we think about this, think about what are the limitations or what are the holdups of being able to even conduct this type of on-farm assessment. So.
Excellent. Good cliffhanger, Matt. And we've got Abby with us now too. So Abby and Matt will be able to answer questions in the breakout room. So hoping for some good discussion there. Thanks, Matt. Can you quit sharing your screen, please?
Never.
Thank you. I have all the power today, telling people what to do, and legitimately. So our last part of the lightning talks is our very own Erica Gentry. She's the communications wizard. That is an unofficial title, but she is our communications wizard here at Discovery Farms, Wisconsin. She has an agronomy degree and grew up on a local farm. She's still very involved with her family's dairy farm, making her uniquely suited to help us interpret agricultural research data and communicate those results. So she's going to share some of the resources from Discovery Farms and kind of wrap up our lightning talks. Take it away, Erica.
Great, thanks, Amber. So first of all, I just want to start out by saying thank you everyone for sticking with us through this webinar series and participating. We've seen it to be a great success, and we hope to offer more opportunities like this in the future. Okay, there we go. If you missed any of the previous webinars, I just want to say they are all being posted on the MAWRC YouTube channel. So feel free to check those out if you missed any or want to go back to get a recap. So I'm just going to give another overview of the Discovery Farms program, some of the resources we have, as well as give some tips for manure application this year in 2021. So at our core, all of our Discovery Farms programs here in Wisconsin and Minnesota, there's also programs in Washington as well as Arkansas, are built on the foundation of farmer leadership, credible on-farm research, and outreach. So we perform outreach in regards of webinars, events in person when we can have them, and we produce a lot of different written materials. So the core of our research is performed at edge of field water quality at sampling sites that look somewhat like this. So this is a good graphic we like to share, and this is an example of a surface monitoring station. So how it's set up is runoff is channeled from the edge of the field through a flume where water can be collected in the gauge house, and then samples are collected by either Discovery Farms staff, or we have a good selection of partners that we work with in local regions to help us collect those samples that are then sent to a lab and analyzed for sediment and phosphorus and nitrogen. And we also have tile monitoring stations that are set up similar to this, but instead of flumes, we are collecting samples at tile outlets. So that data we collect is turned into, as I said earlier, a variety of written materials. We produce publications that go into major ag newspapers, as well as shared through online outlets. We write journal articles showcasing our research findings, and Matt Ruark, who just talked, is our faculty advisor here in Wisconsin. So if you search his name, a lot of times we partner with him on a lot of our research, and he helps us get these journal articles out there. We do quarterly newsletters that we have recently switched to digital newsletters. So we produce those sharing important updates and information about our research. So I hope you all subscribe to receive those updates, and you can do that on our website. We also produce a variety of fact sheets. So we share all this information on our website. So here we have our uwdiscoveryfarms.org website in Wisconsin that recently went through a good restructuring. So we have a new restructured resource library with all those resources. And Discovery Farms Minnesota also has a great website. We share information on a blog, the Ag Water Exchange, and we also have Facebook and Twitter. So check us out. If you're ever curious about what's happening at our monitoring stations right now, be sure to check out real-time data. In Wisconsin, we partner with USGS, the United States Geological Survey, that helps to remotely collect and analyze our data and run our monitoring stations. And these links go to real-time data, which you can get a live look. A lot of our stations actually have cameras that are taking pictures of what's happening, as well as graphs that are set up. And Minnesota works with the Minnesota Department of Agriculture, who helps them with their monitoring. Okay, so one of our main goals here at the Discovery Farms program is to provide you tools for your toolbox as you're making farm management decisions or as farm advisors. So we like to provide a variety of tools versus just one hammer example, so you can have your own strategies that work on your farms, because we know that no farm system is the same, and it's important to have options when it comes to nutrient application and management decisions. So we're going to go through some quick reminders as we get into 2021 and think about our manure applications. So it's important to remember to walk your fields. To walk your fields before you're making manure applications in the winter time. Be sure to watch for melting snow, as that leads to risk of runoff and those nutrients being lost, as well as look for active runoff, saturated soils, dry, cracked soils. This is particularly important in areas with shallow soils and in tile drained land, where manure application on cracked soils could lead to a direct outlet to those tile outlets or groundwater. And also be sure to check your future forecast and see what's coming up. From the data we've collected from our years of monitoring experience at Discovery Farms, we found that March is the month where we see the most surface runoff. So depicted in this graph, March stands out as a risky time period for surface runoff. So we know that surface runoff is going to happen. It just does, but you have the option to control what leaves your field in your surface runoff. So there are two main time periods that we see runoff happening. And those periods are the snowmelt period, which happens from February through April. So this is when we have snowpack here in the Midwest and warming temperatures that are melting that snow, leading to active runoff, which is a time period where we are seeing a lot of water leaving the field. And then there's the rainfall runoff period. So May, June, and July are what we see as typically rainier seasons, and then coupled with early growing season conditions. So oftentimes there is no established crop on the field and no cover to protect that soil and protect nutrients from being lost. So we see water leaving that field, as well as a time for risk. So this graph here is showing how late winter manure applications can potentially increase your phosphorus loss in snowmelt by 2 to 4 times. So on the x-axis, we see total phosphorus loss in pounds per acre, as well as dissolved phosphorus loss on the y-axis, which is the phosphorus that moves actively with water. And then points on this graph are runoff events that we have measured, and they're separated out into events that had no winter manure application and early winter manure application, defined as November through January. And then we have late winter manure applications, defined as February through March. And we see a majority of these points are clustered on the left side of the graph here, under the 2 pound per acre mark. But then we have this handful of points here that are all open circles depicted as late winter manure applications. And so this shows that they were applied at a time of risk, and we saw increased losses of phosphorus correlating with that late winter manure application. So I'm just going to go through some manure application tips through the season. This can also be found on a handout that is on our UW Discovery Farms website. So as we're getting ready to get into our fields before planting, we heard a great presentation last week from Dustin Gorning about the manure advisory forecast, or the runoff risk advisory forecast. And this is a really great tool to utilize as you're getting ready to spread manure, to check your risk and see what the likelihood of runoff happening is. If you're in a high risk time period, it's not a good time to spread manure, as it's at an increased risk to be lost. Make sure you're avoiding manure application shortly before snowmelt or runoff event. And if you do need to apply manure at one of these time periods, if you apply every month of the year, or if you have a pit situation that you need to empty a little bit, make sure to work with your local land conservation or a local professional to help you identify fields of low risk that are good options for spreading during these risky time periods. All right, during the growing season, referring back to what we said was another high month for runoff, which was June. Remember that this period of time is likely to have lots of rain, as well as a crop canopy that is not fully established. So be wary when you're applying manure on those fields. Understand your crop needs or make sure it's best to apply nutrients when the crop is going to need them. So be conscious of what crops you have and when they're going to need a manure or nutrient applications. And then be aware of manure that's spread on tile drained land and use best management practices for that. After harvest, keep in mind cooler temperature soils wait for cool temperature soils when bacteria has slowed down to reduce your risk for nitrogen loss, unless you are applying on a growing crop. So if you have an established cover crop, those can act to help take up some of that nitrogen if you're spreading manure. All right, that is my lightning talk. Thanks for listening. I'm not sure if there's any questions, but I think now what we can try to do is get into some breakout rooms. So I have depicted the breakout rooms here. We're gonna attempt to do this. Bear with us. So in just a minute, I will open breakout rooms, and please join in on which breakout room you are most interested in. And we're just going to kind of treat these as a time for some casual discussion. So if you're interested in talking to Matt about nitrogen use efficiency, join breakout room 1. If you want to talk more with Tim Griffins, join breakout room 2. And then in breakout room 3, there's going to be a representation of us from the Discovery Farms